What you are looking at here is a fully functional USB-C lithium-ion battery charger, and the goal of this project was very simple. Try to make it as small as physically possible. This is an experiment in extreme miniaturization. There is no microcontroller, no firmware, and no unnecessary features. Just the bare minimum circuitry required to take 5 volts from USB-C and safely charge a single-cell lithium-ion battery. This is very likely one of the smallest USB-C battery chargers ever built, and while it is not a production-ready design, it is a great example of how far you can push component density when size is the primary constraint. In this video series, I will walk through the entire process, from the schematic to the PCB layout to the final assembled board. Along the way, I will explain every design decision, every compromise, and every trick used to make this board as small as it is. So if you are interested in minimalist hardware design, aggressive PCB layout techniques, and slightly reckless but genuinely educational electronics projects, you are in the right place. Alright, so let's start with the big picture, even though this project is very much about making everything as small as possible. What you're looking at here is the entire functional block diagram of this project. There's nothing hidden and nothing fancy. It is just the absolute minimum required to charge a single-cell lithium-ion battery from USB-C. And that is completely intentional. This is not a production-ready charger. It is not meant to survive abuse, and it is definitely not something you would ever ship in a consumer product. This is purely a fun engineering exercise, asking a very simple question. How small can a functional USB-C lithium-ion battery charger realistically be? Starting on the left side, we have the USB-C connector providing a 5-volt input. There is no USB power delivery negotiation here, no complex logic, and no communication beyond the bare minimum. We are simply relying on the default behavior of USB-C, where 5 volts are available as long as the CC pins are terminated correctly. Electrically, this behaves just like a classic USB-A power source, just in a much smaller and more modern connector. Moving to the center of the diagram, we have the battery charger IC, which is the heart of the entire design. In this case, it is an LP4054 style linear lithium-ion charger. This tiny chip handles almost everything for us. It regulates the charge current, manages the constant current and constant voltage charging phases, detects when the battery is full, and safely terminates the charge process. It even provides a status output pin that we can use for visual indication. Because this is a linear charger, it is not particularly efficient, and it does dissipate heat, but the advantage is simplicity and size. There is no inductor, no switching noise, and very few external components. For a project focused entirely on minimizing physical size, this trade-off makes perfect sense. Below the charger IC, we have 2 status LEDs. One LED indicates when the battery is actively charging, and the other indicates when the charge process has completed. What makes this interesting is that the charger IC only provides a single status pin. Instead of using additional logic, the 2 LEDs are connected in opposite directions around that one pin. When the charger is actively charging, the pin is pulled low and the charging LED turns on. When charging finishes, the pin becomes high impedance and the biasing naturally shifts, allowing the done LED to turn on instead. It is a simple and elegant trick that fits perfectly with the minimalist nature of this project. On the right side of the diagram, we have the single-cell lithium-ion battery itself, and this is where an important disclaimer comes in. There is no additional protection circuitry here. There is no overcurrent protection, no over-discharge protection, no short-circuit protection, and no load sharing or power path management. This charger assumes that a protected battery cell is used, or that the user fully understands the risks involved. Many features that you would expect in a commercial design are intentionally missing. There is no transient voltage suppression on the input, no reverse polarity protection, no external thermal monitoring, and no battery protection IC. Every one of those features would make the design safer and more robust, but every one of them would also make it larger. And in this project, size is the primary constraint. So when you strip everything down, this entire block diagram really comes down to just 3 things: USB-C power in, a minimal charger IC in the middle, and a lithium-ion battery on the output. No microcontroller, no firmware, and no configuration. Just enough circuitry to prove that yes, this really is a working USB-C lithium-ion battery charger. In the next parts of this project, we will dive deeper into the actual schematic, look closely at how the LED indication works electrically, and explore just how far you can push PCB layout when physical size is the number one goal. If you enjoy slightly reckless but genuinely educational hardware experiments like this, make sure you are subscribed, because this is where things start to get interesting. As you can see, I have already laid out all the components needed for this design. There is nothing extra here and nothing decorative. Every component on this schematic exists because it is strictly required for the charger to function. Also worth mentioning right away, all components in this design are size 0402. That includes the resistors, capacitors, and the LEDs. This is very much intentional since the entire goal of this project is to push the physical size as far down as possible. Starting on the far left, we have the USB-C connector, which is the only power input to the circuit. From this connector, we are using the VBUS pin to bring in 5 volts, and the ground pins are tied directly into the system ground. There is no USB power delivery controller here, and no data communication involved. This is the simplest possible USB-C implementation, relying purely on default 5-volt operation. Connected to the CC pins of the USB-C connector, you can see two 5.1 kilo ohm resistors going down to ground. These resistors are required to correctly identify the device as a power sink. Without them, the USB-C source would not enable VBUS. This is the only negotiation happening in the entire design, and it keeps the USB-C side extremely simple. Moving to the right, we have the 5-volt rail coming out of the connector, followed immediately by 2 small decoupling capacitors. These are 1 microfarad capacitors connected between 5 volts and ground. Their role is to provide local decoupling and keep the input supply stable before it reaches the charger IC. Continuing further right, we arrive at the battery charger IC itself. This is the LP4054, a tiny linear lithium-ion charging IC. This chip handles the entire charging process. The VCC pin connects to the 5-volt input, ground ties into the common ground plane, and the BAT pin connects to the battery. On the ISET pin, a single resistor sets the charge current. With just that one component, we define how much current the battery is charged with. On the battery output side, there are 2 additional capacitors connected from the VBAT node and down to ground. These provide output stability and help reduce noise during charging. Once again, they are kept small and minimal to match the overall goal of the project. On the right side of the schematic, we have the 2 status LEDs. One LED indicates when the battery is charging, and the other indicates when charging is complete. Both LEDs are driven from the same status pin on the charger IC using simple series resistors. Depending on whether the pin is pulled low or left floating by the IC, one LED turns on while the other turns off. This avoids any extra logic and keeps the design compact. Finally, the VBAT node connects directly to the lithium-ion battery. There is no additional battery protection circuitry in this design. No overcurrent protection, no load sharing, and no battery management beyond what the charger IC provides. This is not a production-ready design. It is a deliberately minimal circuit, created purely to explore how small a functional USB-C lithium-ion charger can be. When you look at the schematic as a whole, it really is just the essentials. USB-C input on the left, minimal negotiation, basic decoupling, a tiny linear charger IC in the center, 2 status LEDs, and a battery on the output. Nothing more and nothing less. This is about as stripped down as a USB-C lithium-ion charger can realistically get. The first thing I do here is import the schematic into the PCB editor. At this point, all of the electrical decisions have already been made. The nets are defined, the components are selected, and the connectivity is locked in. From here on, this becomes a purely physical design problem. Every decision is about geometry, density, and how to fit everything into the smallest possible area without breaking basic manufacturing rules. Once the schematic is imported, I start by placing the USB-C connector. This is the largest single component in the entire design, and it immediately defines the minimum board size. I place the USB-C connector on the bottom side of the PCB. This is a very deliberate choice. All of the remaining components will be placed on the opposite side of the board. By doing this, I am stacking functionality vertically instead of spreading it out horizontally. In a design this small, using both sides of the PCB is not optional. It is absolutely required if you want to reduce the footprint. With the USB-C connector placed, I already know that everything else has to fit within its outline. That constraint guides every decision that follows. There's no extra board area to work with, so every millimeter matters. Because this charger is meant to be as small as possible, I decided not to include any kind of battery connector in the schematic. A connector would immediately dominate the layout and defeat the purpose of the project. Instead, I created custom rectangular pads that act as direct battery charging pads. These pads are meant for soldering battery wires directly to the board. Electrically, this is perfectly fine, and mechanically it saves a huge amount of space. To make this user-friendly, I also added clear silk screen markings next to these pads. One pad is marked with a plus sign to indicate the battery positive or VBAT connection, and the other pad is marked with a minus sign to indicate ground. This makes it very clear how the battery should be connected even though there is no connector. Next, I focus on the USB-C resistors. These are the two 5.1 kilo ohm resistors that connect the CC pins to ground and allow the USB-C source to enable the 5-volt supply. To keep the routing as short and clean as possible, I place these resistors directly above the CC pins on the USB-C connector. This placement allows me to drop vias immediately next to the pads and route straight down to the connector with almost no trace length at all. The result is a very compact and very simple connection that does not waste any space. After that, I place the charger IC itself. This goes roughly in the center of the board. From a floor planning perspective, this makes sense because the charger IC is connected to everything. It needs a short path to the 5-volt input, a short path to the battery pads, and reasonable access to the status LEDs. Placing it centrally minimizes trace lengths in all directions and gives me the most flexibility later during routing. Once the IC is placed, I move on to the status LEDs and their series resistors. These components are grouped tightly together and placed as a small array on the bottom side of the board. Keeping the LEDs and resistors next to each other makes the status circuitry very compact and visually organized. It also simplifies routing since all of these parts connect to the same status, pin, and power rails. Placing them on the bottom side helps balance the component density between the two layers and avoids overcrowding the top side. The final step in the floor planning process is placing the decoupling capacitors on the 5-volt input and the battery voltage output. This is one of the trickiest parts of the layout because the USB-C connector has relatively large ground pads that take up a lot of valuable space. I carefully fit the decoupling capacitors into the remaining gaps, making sure they are still electrically close to the pins they are meant to decouple. Even in a design this small, proper decoupling still matters, so these capacitors cannot be placed arbitrarily. The challenge is to keep them close while avoiding interference with the USB ground legs and maintaining reasonable soldering clearances. By the end of the floor planning stage, every component on the board has a very deliberate placement. Nothing is random and nothing is accidental. Each decision is driven by the goal of minimizing board area while still keeping the design manufacturable and electrically sound. With this floor plan in place, the board is already extremely dense, and the next step is routing, where the real challenge begins. When I start routing a board like this, the most important thing to understand is that the routing is not where the design actually happens. The real work was already done during the floor planning stage. If the floor plan is good, the routing almost feels automatic. If the floor plan is bad, No amount of clever routing will save you. So the very first thing I route is the USB-C CC pins. These are simple signals, but they are a perfect example of why placement matters. Because the CC resistors were placed directly above the CC pins on the connector, this routing is trivial. I can drop vias right next to the pads and connect the CC pins to their pull-down resistors with essentially zero trace length. No awkward bends, no crossings, no wasted space. This is exactly what a good floor plan buys you. Instead of fighting the layout, you are just executing it. Next, I route the PRO-G pin from the charger IC to its pull-down resistor. This is a small detail electrically, but it is conceptually important. That resistor value directly defines the charging current of the battery. One resistor decides how hard we are pushing current into the cell. Because of that, I want this connection to be clean, short, and unambiguous. Again, because the resistor was placed deliberately close to the IC, the routing is short and direct. There is no guessing and no compromise. The schematic intent is preserved perfectly in the layout. After that, I connect the STAT pin to the LEDs. This is another area where good placement completely removes complexity. The LEDs and their series resistors were grouped together intentionally, so routing the STAT pin to both LED paths is straightforward. There is no spaghetti routing and no backtracking. The traces are short, clean, and easy to follow, which matters not only electrically but also when someone else looks at the board later and tries to understand what is going on. Once the critical signal routing is done, I move on to power, starting with the 5-volt input on the top layer. Instead of routing this as individual traces, I draw a polygon pour for the 5-volt rail. This immediately reduces impedance and saves space. The polygon naturally wraps around the charger IC, the input decoupling capacitors, and the series resistor for one of the LEDs. Because the decoupling capacitors were placed correctly during floor planning, they land directly inside the 5-volt copper area, exactly where they should be. There is no need for long traces or awkward jogs. The copper itself becomes the connection. Then I do the same thing for the output side. I draw a polygon for the battery output voltage. This polygon connects the charger IC output, the output decoupling capacitors, and the custom charging pad that I created for the battery. This is a great example of how layout and mechanical decisions overlap. Because there is no connector, the charging pad itself becomes part of the power distribution network. The polygon makes that connection low impedance and mechanically robust at the same time. After finishing the top side power routing, I move to the bottom side to route the USB-C connector. I start with the 5-volt rail coming out of the connector. This trace needs to be reasonably thick, even though the board is tiny, because this is where all of the charging current flows. I keep the trace wide and short, and then I add 2 vias that bring the 5-volt rail up to the top layer where it connects directly into the 5-volt polygon. This way, current can flow vertically through the board instead of being forced to snake around horizontally. Once the power rails are in place, I pour ground polygons on both the top and bottom layers. Ground is not something you route as an afterthought. It is a structural element of the PCB. By having solid ground pours on both layers, the board becomes electrically quieter, mechanically stronger, and much easier to work with. For all ground pads, I make sure they have direct thermal connections to the ground polygon. In a board this small, thermal reliefs are not helping you. Direct connections reduce impedance and make the ground network behave more like a solid reference plane. It also simplifies the layout visually because everything ground related just merges into one continuous copper area. The final step is adding stitching vias across the board. These vias connect the top and bottom ground polygons together. Electrically, they reduce ground impedance and improve return paths. Mechanically, they help tie the board together, and practically, they just make the whole design feel more solid and intentional. Even on a tiny board like this, stitching vias make a noticeable difference, and this is really the core lesson of the entire rent. When the floor plan is good, the layout is not a fight. You are not constantly rerouting traces or making compromises. You are just following the logic that you already established earlier. And this is the final result. A fully functional USB-C lithium-ion battery charger reduced down to the absolute minimum. No unnecessary features, no extra circuitry, just the essentials packed into the smallest footprint possible. This project was never about making the safest or most feature-rich charger. It was about exploring how far you can push PCB layout and component density when size is the primary constraint. If you enjoyed this kind of extreme miniaturization and layout focused design, there is more coming. Thanks for watching.